So just going to look at the past, I think 3 years I've got here. Past 3 years of HSC questions. So you can see the sorts of things that they'll ask for conics. Didn't include the multiple choice ones. Some of them we might have already seen in our morning starters anyway. But let's have a look at the ones we're working out or involved. So last year in question 13, so remember there's 10 multiple choice, then we have 6 15-mark questions after that. So 13's about midway there, isn't it? Diagram gave us 2 hyperbolas, which they've cleverly called H1 and H2. The first one it equals 1, the second one it equals -1. Okay, so P lies on the first one, and then Q, well, we don't know where it lies because the first part is to verify that Q lies on the other one. So, bit of a gift mark to start the question, because all we've got to do is substitute it into the equation of the hyperbola. Hopefully, we'll come up with, in this case, it was -1, wasn't it? So sub that in, a squared tan squared on a squared, b squared sec squared on b squared. They cancel, tan squared minus sec squared, -1. So fingers crossed, yes, we got that mark. Next part, show that the equation of the line PQ, well, we've got the coordinates. So other than the strange coordinates with trig, this is really a 2-unit question. You know? It's just point slope formula. We just got to work out the slope between the 2 points and sub in. So slope of PQ turns out to be minus B on A. Point slope formula, and put it in the form that they're looking for. And we've got that. So again, fingers crossed, hopefully we've picked up 2 marks. Yes. I'm assuming they were worth 1 each. Oh, now this one's a little bit more tricky. Prove that the area of the triangle OPQ is independent of theta. So when we work out this area, there should be no mention of theta in it whatsoever. Okay. What area of a triangle? Well, there's 2 ways of doing it, isn't there? We've got half base times height, or we could use our half AB sine of the angle in between. Looking at the diagram, I think I'm going to go half base times height, because I can work out the length of PQ, and I can easily find the perpendicular distance from O to PQ as well. So I can do the base times height one. Perpendicular distance from O to PQ turns out to be, there it is, AB tan theta plus sec theta on the square root of A squared plus B squared. And finding the distance from P to Q. Well, sec theta minus tan theta squared is actually the same as tan theta minus sec theta squared. Because just one's negative, one's positive, but when you square it, they're both going to be the same thing. So I could actually factorise that. It doesn't matter which one I use, sec theta or minus tan theta or tan theta minus sec theta. I chose tan theta minus sec theta because I'm looking ahead to, I'm going to go half base times height. And the other one is tan theta plus sec theta. So I'm thinking, oh yeah, I'm going to multiply, difference of 2 squares. It would make sense to have tan theta minus sec theta rather than sec theta minus tan theta. So half base times height, we get half AB tan squared minus sec squared, but tan squared minus sec squared is 1. So there we are, half AB, there is no mention of theta in the area of our triangle. So a bit of manipulation to get that one out. Let's go the year before. Again, question 13, about the middle of the paper. So this time we've got a hyperbola. So our standard one there. We've got 2 points. P is AT, BT, and Q is A on T, and minus B on T. Those points aren't actually on the hyperbola. They're on the asymptotes of the hyperbola. So now that makes sense why they gave them those coordinates, because remember, the actual equation of those asymptotes would be y equals b on ax, and y equals minus b on ax. Point M is the midpoint. Show that M lies on the hyperbola. So we've got to get those coordinates, substitute it into the equation of the hyperbola, and see what happens. So there's the coordinates they gave us for the midpoint. X squared on A squared minus Y squared on B squared. Ooh. Play around with that. The a squareds and the b squareds cancel. I get a common denominator of 4t squared. So I have t squared plus 1 squared. Oh, gosh, I should have noticed that. Look, I expanded the whole thing out. But I could have gone perfect square minus perfect square. So I would have been left with 4 times the product. So I could have gone straight to 4t squared there. But anyway, we come up with 1, and that's what we're looking for our answer. So yes, M is on the hyperbola. Prove that the line through P and Q is a tangent to the hyperbola at the point M. Okay. So how I approach this one is I say, well, okay, let's find the slope of PQ. So that turns out to be B, t squared plus 1 on A, t squared minus 1. I then wanted to find the derivative because what I want to basically say is this is going to be the slope of the tangent. So dy dx is b squared x on a squared y. At M, substituting in, we get, sure enough, the same slope. So the slope of PQ is the same as the slope of the tangent. Now, this does not prove that the line through P and Q is a tangent, or does it? All I've proven is that the slope PQ is the same as the slope of the tangent at M. So that would prove those two lines are parallel. Can I say they are the same lines? Yeah. Oh, some people shaking this way, some people going this way. We can, because we've already established M lies on the line PQ. Remember, it's the midpoint. So we know PQ is at least parallel at M, but because we know M lies on the line PQ, then they're not parallel. They are, in fact, the same line. This is probably looking a familiar sort of question by now with all the different geometrical ones we've been doing. Show that OP times OQ is OS squared. All right. OP times OQ, I've just used the distance formula. It's nice when they make it join up to the origin. So we get square root of a squared t squared plus b squared t squared for OP, and a squared on t squared plus b squared on t squared for OQ. Okay. We got common factor of t squared, which I can take out the third, becomes t. And then in the second one, 1 on t, so obviously they will cancel. But leaving me with a squared plus b squared in the first one, but also a squared plus b squared in the second one as well. So square root of a squared b squared times square root of a squared b squared is a squared plus b squared. We're talking about a hyperbola. Remember, in the hyperbola, e squared was equal to a squared plus b squared on a squared. So in other words, if I rearrange that, I get a squared plus b squared is a squared e squared. Well, hang on. OS squared, OS is the distance to the focus. And we know the focus is AE. But there was more to this question. Now, if P and S have the same x coordinate, show that MS is parallel to one of the asymptotes. Right, so P and S now have the same x coordinate. So AT is equal to AE, because we know the x coordinate of the focus is AE, and the x coordinate of P was AT. So in other words, T is equal to E. I now know T is equal to E. So the slope of MS, all right, let's do that one. Slope formula, B outside E squared minus 1 on 2E over, etc. But look, something nice happens here. When I play around with this, the bottom, or the denominator to use the fancy maths word, A outside of E squared plus 1 is on 2E, but that would become minus 2AE squared, when I make that all one fraction. So I have an AE squared minus 2AE squared gives me minus AE squared. So I end up now at the bottom being 1 minus E squared. 1 minus e squared cancels with the e squared minus 1, and we get minus b on a, and that was the slope of one of the asymptotes. So yes, ms is parallel to that particular asymptote, y equals minus b on a x. That particular year they had a second conics question. So now question 14, and it was an ellipse question. So the point a cos theta, b cos theta again, so our standard parametrics, standard parabola. What else have they told us? The acute angle between OP and the normal is phi. Okay. Show that the tan of phi is this lovely expression. So what do we know? We know that phi is the angle between two lines. They're asking us to find tan phi. So it sounded like I'm going to use my angle between two lines formula. So remember, that would be tan of the angle is equal to, just need to work out the two slopes to put into this. One will be the slope of the normal, and the other would be the slope of OP. If I've got those two slopes, I'll be able to substitute in. So let's do that. Going to have to do some differentiation to find the slope of the normal. So there's dx to theta, there's dy to theta, dy dx, there's my, no, that would be the slope of the tangent. So the slope of the normal is a sine theta on b cos theta. We now need to find the slope of OP, but again, it's joined up to the origin, so that's quite easy. B sine theta on a cos theta. Okay. Angle between two lines. Absolute value of slope 1 minus slope 2 on 1 plus slope 1 times slope 2. Oh, fractions on fractions, but if we have a look, the denominator will end up being the same. We've got a cos theta, b cos theta, and that also is a cos theta, b cos theta. So if I multiply everything by that, I end up with a sine theta cos theta on b minus b sine theta cos theta on a on, oh, look at the bottom of that fraction, isn't that lovely? Cos squared plus sine squared, which is, of course, yes, I was expecting a quicker response than that, but there we go. AB, so I can factorise out the AB, I wanted that. On the top of the fraction, we've got a common factor of sine theta cos theta. Now, this is where I think, if I remember correctly, I disagree with the answer, because I believe it should be the absolute value of sine theta cos theta. So I'm stubborn. I've left absolute value there. Right. But to get the answer that they required, I've said, well, look, if P is as illustrated, theta would be acute. And so if it's acute, then I know sine theta is positive and cos theta is positive. So it would be the answer that they're looking for. But if it wasn't, that wouldn't be the answer. They made a mistake. I'm convinced. All right, we're going to find the value of theta for which phi is a maximum. Okay. We've just found an expression for tan phi. We want to know when that is a maximum. But it involved this constant. What was our constant? It was a, there it is, a squared minus b squared over ab. That's not going to change. Right? But it's times sine theta cos theta. So basically, I want to know when sine theta cos theta. Well, I know sine theta cos theta is a half sine 2 theta. And I think that'll make life a lot easier, because when is a half sine 2 theta a maximum? Pi on 2, but that would be 2 theta. We want to know theta, so it'll be pi on 4. Pi on 4. That, as I say, is a constant. So the maximum for tan phi will be when it's pi on 4. And oh well, technically, okay, there you go. As it is an increasing function, because if it moved up and down, then maybe that wasn't the maximum. There could be another maximum, but we know it's continually increasing. So that will be the maximum between 0 and pi on 2. All right, let's have a look at the 2013. This was a fun one. I think this is the last one we're going to look at. 2013 question 12 was a rectangular hyperbola question. Again, the standard sort of ones. They've told us absolute value P and absolute value Q are not the same. So that basically means P and Q are not the same point, but also, because they've said their absolute value, it means they're not symmetric, so they won't line up through the origin. You know what I mean? And you can see that from their diagram, that indeed they don't line up. All right, the tangent to the hyperbola at P intersects the x-axis at A, y-axis at B. Similarly, the other tangent at C and D. Okay, they've got a nice dotted circle drawn in there for some reason. Show that the equation of the tangent is the first part of the question. There's our gift mark, our standard. Okay, find the equation of a tangent. So we'll differentiate. We want to know at the point when x equals CP. There's the slope, minus 1 on P squared. Point slope formula. Show that A, B, and O all lie in a circle with the center P. Right. Triangle AOB. If you look at the diagram, it's a right angle triangle. Because A is on the, which one, x-axis or y-axis? X. B is on the other axis. O is the origin. So triangle AOB must be a right angle triangle. Now any right angle triangle, you can draw a circle around it where the hypotenuse is the diameter. And so that's what we've got. We've got a right angle triangle. AB is the hypotenuse. The other thing we had to prove was the center was P. So we know it's a circle. AB is the diameter. The center of the circle will be the midpoint of AB. All right. Well, A, there's my coordinates. B, my coordinates. So the midpoint, what do you know? CP, C on P. Yep, P is the midpoint of AB. So it turns out to be the center of that circle. Interesting question. Now we have to prove BC is parallel to PQ. Now I've redrawn, well, I didn't draw it, of course, rescanned the picture so we can look at what we're talking about here. So we now know there's a circle that goes through A, B, and O. P is the center. But remember, all we knew was that was a tangent. That means there's also a circle over here, because I could have done the same thing with this tangent. And it will go through COD, and Q will be the center. I'm just going to join up there B and C, P and Q, A and D. All right. Now, if P is the center of a circle passing through ABO, okay, we've proven that. And as I say, the same situation must occur on the other one. Q is the center of a circle that goes through DCO. What does this mean? Well, it means AP equals BP. They're both radii of that particular circle. But it also means DQ is equal to CQ. They're the radii of that second circle. So the ratio of AP to BP is the same as the ratio of DQ to CQ. They both equal 1. Well, if those ratios are equal, those three lines must be parallel. Ratio of intercepts of parallel lines. So BC is parallel to PQ, is parallel to AD, but I only needed BC is parallel to PQ, but there you go. It must also be parallel to AD. That, I think, is a very quick way of doing that one.